Hello. Thank you for joining the Texas Instruments New Product Update webinar. Just a reminder that this is a weekly series every Thursday at 10 a.m. Central. A few quick announcements before we get started. This webinar will be recorded and available online at ti.com/MPU. All phone lines will be muted, so if you have questions, please use the chat box and we will try to answer in real time, or you can contact your TI salesperson or field application engineer. Today's topic is speed up time to market, increase power density with these pin-to-pin buck modules. I will now pass it over to Christine Chaco for introductions.
Thanks, Kelly. Hi, everyone. I just wanted to welcome you today to today's meeting. My name is Christine Chaco. I'm a product marketing engineer on the switching regulator team. I'm joined here today with Denislav, who's an applications engineering manager on the switching regulator team, and he'll be here to answer any questions you might have in the chat. So like Kelly mentioned, the title of this presentation is Speed Up Time to Market with an Increased Power Density with Buck Modules. So I'll go into the agenda. So first, I'll be going over two of our latest Buck modules that we've released. The first being the TPSM 33625, which is a 36-volt 2.5 amp Buck module, and the TPSM 365R6, which is a 65-volt 600 milliamp Buck module. And when I say Buck module, I mean a buck converter that's has an integrated inductor and capacitor within its package. Next, I'll be going over the benefits of using a buck module solution over using its converter counterpart. Some of these benefits include that passive integration that I mentioned, which allows for a smaller solution size. Next, I'll be going over the latest advancements in buck module technology and how the modules have regressed over the years. And this includes stuff like improved DMI performance, low IQ, and high efficiency at light loads. And again, Denislav will be in the chat for to answer any questions you might have throughout the presentation. So here is an overview of the benefits of the two devices we're talking about today. Both the TPSM 33625 and the TPSM 365R6 are pin-to-pin compatible buck modules that have different operating voltages and currents, meaning that designers can scale their designs across different power needs. Some of their key features include great EMI performance because of the FCOL packaging that we've used. FCOL stands for a flip chip on a lead frame, which means we've gotten rid of the bond wires between the die and the lead frame, which helps to reduce EMI. It also allows for a smaller package overall. There's also integrated boot caps and spread spectrum capabilities to help decrease noise. With the integration of the inductor and boot cap, we've also helped decrease the overall BOM count to use these devices, which also helps cut down design time and allows your products to be released as soon as possible. These devices also have great IQ performance. The TPSM 33625 has an auto mode, which enables frequency foldback when operating at light loads and allows for an ultra-low current consumption at no load. And like I mentioned earlier, mounting the die directly to the lead frame allows us to keep the package small. So both of these devices have an area of 15.75 square millimeters. So here's the highlight page for the TPSM 365R6. This is the 65-volt 600 milliamp buck module. I wanted to highlight the mode pin that allows you to choose between FPWM mode with fixed frequency over the entire load range, or PFM mode for better efficiency at light loads. It also has a pre-bias startup and overcurrent and temperature protections that make it versatile among a wide range of industrial applications. This is the highlight page for the TPSM 33625. The mode pin here allows you to enable auto mode, like I mentioned earlier, for low IQ and no load. And the RT pin variant can be synced to an external clock between 200 kilohertz and 2.2 megahertz to avoid noise-sensitive frequency bands. And this device also has dual random spread spectrum to help reduce EMI. So in the slide, I wanted to reiterate the pin-to-pin compatibility of these two devices. We really want to make sure that this family was useful and helpful to a wide range of applications. So we wanted to include a 65-volt device with a lower current, and then a 36-volt device with a higher current. So the same design can kind of be scaled across different applications. So now I'm going to go over the benefits of using a buck module when compared to a standalone converter, and highlight some of the benefits that aren't obvious based on some of the specs that I mentioned earlier. So when you talk about the cost of using a buck regulator, you have to think about, of course, like the BOM costs, which includes the price of the IC and the extra passives like inductors, capacitors, resistors. Sometimes sourcing these passives can be difficult, or designers have to resort to using the components that are already on hand, even if they aren't necessarily the correct components. You also have to think about the PCB costs, which include the amount of space taken up on the board, the via costs if you're thinking of EMI mitigation, and the cost to place each component on the board. And then lastly, you'll have to think about the design time costs, like the time and money it takes to support the R&D team, and the opportunity cost of withholding a product from being released to the market due to longer design times. And most of these, if not all of these costs, can actually be lowered when you decide to use a buck module instead of a standalone converter for your power management solution. For the materials costs, using a buck module helps cut down on the BOM count and helps with the heavy lifting of sourcing materials. Our competitive pricing can help give you a better deal on the passives than if you were to buy them separately. PCB costs are also cut down due to the small package of these buck modules. The integrated passives also allow you to take up less space on the board, and they're also thoughtfully placed within the module to help with EMI. And the design time is also cut since less validation is needed during the component selection process, which gives time back to the designers to focus on other critical challenges during their design process. So here, I'm just reiterating some of the benefits you'll notice when you design with our buck modules. So first, we choose the optimal converter with the best fit passives based on the intent and functionality of the switching regulator. We also characterize the modules thoroughly to give you an accurate understanding of the electrical characteristics with the integrated passive, so with that inductor and boot capacitor. We also integrate the latest technology found in our converters and to bring power density and functionality together in one package. Okay, so now I want to go over an example design to compare a module to its converter counterpart. Here I have a 24-volt input, 3.3-volt output, 6.6 watt design. And I'll be comparing the TLVM 23625 which is the same as the TPSM 33625 but without spread spectrum, to the LMR 43620Q1, since they're comparable switching regulators inside. So when you look at the efficiency of this design, it hovers around 86 and 87% for both the module and converter, while the solution area for the module is actually almost half of what the converter solution is at 82.6 millimeters squared. The solution BOM count has actually decreased by 2 for the module because of that integrated inductor and extra boot capacitor. And although the 1K price of the module is a bit higher than the converter at $1.50 versus $1.03, if you look at the BOM cost, they're pretty similar. And based on this, I'd say that the time and effort saved during the design process when using a module makes that those extra few cents worth it. So finally, I wanted to go over some of the latest advancements in buck regulator technology that have helped make modules a better choice for a wide range of industrial applications. So here I'm summarizing the 3 big features that we probably show off in our power modules. All of our modules have features that help mitigate EMI as much as possible. And we've already talked about the integrated boot caps and spread spectrum as some of these features. We also have a dual input path and resistor adjustable switch node slew rate to also reduce noise. The graph on the left is the results of a conducted EMI test on the TPSM 365 R6 with an EMI filter added, and you can see that the module passed with plenty of headroom in comparison to the standard line. The next big benefit is the small package that our modules come in. Modules will almost always be the best option when small solution size is a priority for a design. And recently, with the innovation of FCOL packaging, we're able to get the package sizing comparable to our converters, which is important as space-constrained projects are becoming more of the norm. The last innovation is great for projects that require low power consumption during standby, like battery-powered projects. So the graph on the right shows the IQ for the TPSM 365 R6 when switching with no load and then also during shutdown. And you can see the IQ doesn't reach any higher than 10 microamps across its input voltage range, which is great for overall power consumption of our product. Next, I wanted to show a timeline of some of the package advancements that were made on the larger scale of the entire switching regulator portfolio. So looking at this timeline, you can see how we've advanced our package technology. We started out, of course, with our leaded packages, and slowly, as we wanted to decrease size, we got rid of the leads. And then here, you can see a little graphic showing how we've removed the wire bonds in our FCOL packaging and actually mounted the die directly to the lead frame. We've also worked on optimizing our thermals and improving EMI in other ways. And all these advancements have kind of culminated into what we know our power modules to be today. Yeah, this is kind of just how some of our package evolution. I included this last slide to really demonstrate how far our buck modules have come and how comparable they are in size to our converters. So this picture on the left is actually a demo board that shows some of the sizing of our older modules. And so you can really see how big some of these packages were at 15 by 18 millimeters, and a lot of them had leads like this. But over time, we've been able to shrink that package down to what you see on the right in the top right of this picture. These are our latest modules. This one being the TPSM365R6, which is the 65 volt device I was talking about. And again, in the same package, the 36 volt device is right here. And you can see that these package sizes are very similar to what you'll see with a converter. But with these modules, you have that integrated inductor and boot cap many times. So. This last slide is just has a few links for you to help get started on designing in one of these devices. I've also included a training video about the value of buck modules, and here we have the link to WebBench, which allows you to simulate or kind of create a design based on your product specifications. We also have EVMs available to purchase so that you can begin testing with these modules. I just wanted to thank you all for attending this meeting, and I hope this was helpful for you to understand the usefulness of using a buck module and a little bit more about 2 of our latest modules. Thank you.
All right, thank you, Christine. And thank you for attending today's MPU webinar. The recording and PDF version of the slides will be available at ti.com/MPU. See you next week for our next topic, industry's smallest fully integrated USB Type-C and PD and buck boost converter solution. Thank you, everyone, and have a great day.